So if you're anything like me, when you learn the material at the end of the last section, you might have gotten a little bit worried. The fact that the derivative of a product is not the product of the derivatives is kind of troublesome because you can kind of just skate by and be like, yeah, things work out the way I'd expect them to work out. After I learned this power rule, everything just kind of fell into place. The derivative of sum, sure, of course it's the sum of the derivatives. What else would it be? The derivative of a number times a function? Well, that's probably just the number times the derivative of the function. Yeah, it is. Cool. That's what I would have guessed. And no matter how much someone tells you to be really careful when you're doing derivatives, until you come up with a non-example, like the one that we ended the last video with, it's hard to really understand why. What I want to do in this video is a bunch of examples, but before I do, I want to kind of summarize what we've learned so far. So our big takeaways are these rules that you have in front of you. This first one here is what's called the power rule. These next two are much less important, but they're good facts to know. You can almost think of them as consequences of the power rule, although it doesn't quite work out. But if you thought about this x is x to the 1 power and brought the 1 down in front and then made it 1 times x to the 0 power and recognized that x to the 0 power is basically 1, you might be able to talk yourself into this fact. Similarly down here, if you thought about this as a constant times x to the 0 power, when you bring that 0 down in front, it kind of makes everything go away. That reasoning doesn't quite hold up concretely, but maybe it gives you another way of thinking about these two little facts. Anyways, in addition to this power rule, we had these two rules that we can write with some shorthand. When I'm taking the derivative of a constant times a function, all I have to do is bring the constant out in front and multiply that by the derivative of the function. And if I'm taking the derivative of a sum of two different functions, all I have to do is take the derivative of each function individually and add up my answers. I'd be remiss if I didn't point out to be a little bit careful with this last one here, because while this fact does hold for addition and subtraction as a consequence of this rule, it does not hold for multiplication. The derivative of f of x times g of x is very much not equal to the derivative of f of x times the derivative of g of x. You can memorize all these symbols, but for me anyways, it's easier to kind of think about what's going on than to just memorize them. So having like a little translation of what these formulas say is kind of useful. When you're using the power rule, essentially what you do is you bring the exponent down in front, and then your new exponent is 1 less than your old exponent. So think if you're taking the derivative of x to the 5th, you first write that 5 out in front, that's the bringing it down in front part, and then you're still going to raise x up to some power, it's just the new power will have an exponent 1 less than your old power was. So instead of writing a 5 here, I write a 4 right here. Similarly, for constant multiples, you can pull the constant multiples out in front, and what I mean by that is if instead of the derivative of x to the 5th, it was the derivative of 10 times x to the 5th power, we could think about this as 10 times the derivative of that x to the 5th power. Note, we're not taking the derivative of the 10, we're pulling that constant multiple out in front of the derivative symbol, and then just multiplying the answer to our derivative, 5x to the 4th in this case, by that 10. So our final answer would be 50x to the 4th power. Don't confuse this case down here where we pull constant multiples out in front with this case down here that says the derivative of a constant is 0. I don't know why that's indented so weird. If we were taking the derivative of 10, our answer would be 0. But up here, we're not taking the derivative of 10. We're taking the derivative of 10 times x to the 5th, and when we employ this rule, we bring the 10 in front of the derivative symbol, which prevents us from having to take the derivative of the 10, which would have produced the 0 had we taken that derivative. I think that can be really subtle. More rules to remember is that the derivative of a sum is the sum of the derivatives. That one just kind of rolls off the tongue, but it's worth taking a minute to really unpack what that means. When you're taking the derivative of something plus something, that's the same as adding together the derivative of something and the derivative of something else. Those facts, along with the fact that the derivative of the variable is 1 and the derivative of a constant is 0, summarizes all the stuff we've learned so far. Let's see if we can use that to answer a bunch of examples. 8 of them, I guess. So I better go pretty quickly. The first one, hopefully it's fairly straightforward to you. Show as many steps as you feel are necessary. If I were doing this, I would probably do the constant multiple rule and the derivative of a sum rule all in the same step. I'd say that this is equal to 10 times the derivative of x to the 5th power minus 6 times the derivative of x cubed plus the derivative of 25. I recognize that you could probably get your final answer without writing this step, but I'd encourage you to write this one step in between this line and your final answer, where we recognize that since the derivative of x to the fifth is 5x to the fourth, and 5 times 10 gives me 50, I could say that this is 50x to the fourth power minus 18 coming from this 6 times the 3 when I bring it down in front using the power rule, x to the second power, plus the derivative of 25, which is just 0. You don't have to write the plus 0 at the end if you don't want. We could leave our final answer just like this. You're like, yeah, I get it. Move on to another one. Okay, I will, but I want to make the point at how awesome it is that we can get this answer so quickly and that you maybe are thinking, man, that's pretty easy. Because this problem would have not just been hard, it would have been miserable had we tried to tackle it using our old methods without these new rules. What about this problem down here? It's actually going to work out pretty similar to the example we have up here. There's just a couple algebraic difficulties that you run into that I want to give you practice on. I'd again show at least one line of work. So I would say that this is 4 times the derivative of x to the 10th power minus 6 times the derivative of x to the 9th power plus 2 times the derivative of x squared. Nothing interesting has happened so far. But when we get to this next term, negative x divided by 2, you might be thinking, wait, I don't have a rule for taking the derivative of a quotient, something divided by something. That's true. So what do you do when you're supposed to take the derivative of something that you don't have a rule for? Well, the only trick we've seen so far is to rewrite this in a form that's conducive to the rules that we do have. This is where algebraic skills come in so handy. If you can recognize that negative x divided by 2 is the same as negative 1/2 times x, then this problem's not that hard. The challenge with this problem is not the calculus at all, it's the algebra. If instead of writing what you see inside this green box, I wrote this problem's simple. You pull out the negative 1/2, and you multiply that by the derivative of the x. No challenges with this term at all, but because of the way it's written, it's not simple at all. So recognizing that these two things are equal is imperative. In case you're not sure about why they're equal, really what we're doing here, we have negative 1/2 times x, and when you're multiplying together a fraction and a whole number, sometimes it helps to think about it as multiplying together two fractions. The way you make the x a fraction is you think about it as x divided by 1. And now when you multiply straight across, a negative times a positive is negative, 1 times x is x, 1 times 2 is 2. So negative x over 2 is the same as negative 1/2 x. But writing it in this form with coefficients is much more conducive to the derivative rules that we have. Be careful with this last term. Yeah, in a sense, it's something divided by something, but instead of thinking about this as 3 divided by 5, think about this as a number, the number 3/5. This is just a constant over here, even though it might look like division. It's just the derivative of that constant. Can we jump straight from here to the final answer? I think that's reasonable. The derivative of x to the 10th is 10x to the 9th. The 10 and the 4 give me 40, so I get 40x to the 9th power. The derivative of x to the 9th is 9x to the 8th. The 9 times the 6 is negative 54x to the 8th power. The derivative of x squared is 2x. This 2 times that 2 gives me 4x. The derivative of x is just 1. So I have negative 1/2 times 1, in other words, negative 1/2. And the derivative of 3/5, because 3/5 is just a constant, is 0. So I have a plus 0 at the end, which I don't even have to write, and I get this as my final answer. Moving right along. Can we take the derivative of 6 over x squared plus 2/3? Well, yes, but not when it's written in this form. What you have in this first term is something divided by something. We don't have rules for that. Not yet anyways. But maybe we can rewrite this so that it's in a form conducive to our rules. 6 divided by x squared is the same as 6 times x to the negative 2 power. And much like up here when we rewrote negative x over 2 as negative 1/2 x, we want to rewrite 6 over x squared as 6 times x to the negative 2 power so that it's easier to employ our different derivative rules. The derivative of a sum is just the sum of the derivatives, so I take the derivative of this thing and then I add the derivative of this thing. For the derivative of this thing, I could pull the 6 out in front and then just take the derivative of the x to the negative 2 power. You could probably do all of that in a single step, but I'm going to show one extra step just in case people are struggling to see all this stuff. When in doubt, show more work. The derivative of 6x to the negative 2 plus 2/3 is 6 times the derivative of x to the negative 2 plus the derivative of 2/3. What's that equal to? Well, we'll use the power rule over here, bring the negative 2 down in front. Negative 2 times 6 gives me negative 12. The x will now be raised up to 1 less than this power. Be careful, it's tempting to think that 1 less than this power is negative 1, but it's not. 1 less than negative 2 is not negative 1, it's negative 3. Think number line if you want. 1 less than means a step to the left. Negative 2 is right here. 1 less than negative 2 is negative 3, not negative 1. What about over here? What's the derivative of 2/3? 2/3 is just a constant. The derivative of any constant is 0. Tack on a plus 0 if you feel like it. Leave it off if you feel like it. I don't really care. I think this is a perfectly acceptable answer. However, your next math teacher might be a little bit mad at me if I don't point out that you might want to rewrite this as negative 12 over x cubed, because in the question we didn't have negative exponents, so the standard is to write the answer without negative exponents. But really, for our purposes, either one's fine. All right, what about D here? The derivative of negative 46 times the square root of x plus the square root of 3. There's at least two tricks here. The first one is this is written in radical notation instead of exponent notation. Radical notation we do not have rules for, but exponent notation we do. So you might want to think about this as negative 46 times x to the 1/2 power plus the square root of 3. Wait a minute, why didn't you make that 3 to the 1/2 power? Why'd you leave it as the square root of 3? Because I don't need to make this 3 to the 1/2 power, because the square root of 3 is a number. It's not a function. I purposefully wrote something here that would kind of look like a function so that hopefully you would be like, all right, 3 to the 1/2 and bring the 1/2 out in front and somehow try to use the power rule here. You cannot use the power rule here because the power rule only works when you have x raised up to a power. And here we have 3 raised up to a power. If you can't use the power rule, what can you use? You use your constant rule. The square root of 3 is just a number. Plug it into your calculator if you don't believe me. What is it, like 1.7 something, I think? I don't know what it is. It doesn't matter what it is. It's a number, and the derivative of any number is just equal to 0. So when I'm taking the derivatives, I'm going to have negative 46 times the derivative of x to the 1/2 power. You can write that in a separate step if you want, but I'm not even going to bother. I'm going to say when I move the 1/2 out in front, negative 46 times 1/2 is negative 23, because multiplying by 1/2 is the same as dividing by 2. And when you divide 46 by 2, you get negative 23. I still have the x. That's raised up to a power. What power? 1 less than 1/2. Be careful here. It's tempting to think that 1 less than 1/2 is 1/2, but it's not. 1 less than 1/2 is negative 1/2. Again, if you need to, do a number line argument. Here's 1/2 right here. 1 less than 1/2 is negative 1/2. You might be like, you're not done. You still have to add the derivative of the square root of 3. True, but the square root of 3 is a constant, so its derivative is 0. So I have a plus 0 here, which I don't even have to write. Leave your answer like this. We're good. Change your answer to this. I'm impressed. But really, either way is fine. What about E? Should I even do E? I could probably leave E as an exercise for you. Maybe I'll at least do the first step and then see how I feel. This thing looks like a mess. It looks super hard. And frankly, written in the form that it's written in, it is pretty hard. But if you just rewrite the question, you don't do any calculus at all, you just rewrite the question in a form that's conducive to our rules, it'll make life so much easier. Instead of 5 divided by x cubed, it's 5 times x to the negative 3rd power. Instead of minus the cubed root of x to the 5th divided by 7, think about it as minus 1/7 times x raised up to the 5/3 power. That's not obvious at all that this is the exact same as this. Take a second and make sure that you're convinced of that. And if you're not convinced, go really slowly and understand why those two things are the same, because it's going to be so important that you can rewrite things in other forms, not just for this section, but for the rest of the class. Okay, I'm writing things in different forms. How do I rewrite this mess in a different form? You don't. What? You got to be kidding. Why do I not have to write this in a different form, but I have to write this in a different form? Because this is just a constant. It doesn't look like a constant. It's me, your mean math teacher's best attempt at really trying to confuse you. This looks like a function, but it's not a function. The variable x is never in here. This is just I don't know what number this is, but your calculator knows. If you have the desire, you could take 5 and raise it up to the 10th power. That's some ungodly huge number. And then add 3/2 to that, and then take the square root of that. I don't give you an answer. I have no clue what it is. And frankly, I don't care what it is. It doesn't matter what it is. The point is it's a number. It's a constant. If it's a constant, you don't have to rewrite it, because when you take the derivative of a constant, it's just going to be equal to 0. I really don't have to go any further. I bet you could finish things up from here, but it's going to take all of 30 seconds to finish this problem, so I might as well finish it. Use the power rule over here, bring the negative 3 down in front. I get negative 15x to the negative 4th power. Be careful, not the negative 2 power. Bring the 5/3 down in front. I get negative 5 over 21. That's the product of negative 1/7 and 5/3. Times x raised up to whatever 1 less than 5/3 is equal to. 1 less than 5/3 is 2/3, because 1 less than 5/3 is 3/3 less than 5/3. Then to that, I add the derivative of this huge mess out here, which beautifully is just 0 because that's all a constant, so I don't even have to write it. I think this is a perfectly acceptable answer, but I'm going to make the point that you could rewrite your answer this way. Not just for the benefit of your next calculus teacher, but because seeing that you can rewrite your answer this way reinforces the ideas that you can change exponent notation into radical notation and that you understand how negative exponents work. And while I don't think that's super important for the answers, that is super important for the question, right? We needed to be able to rewrite this thing in this form so we could take its derivative. So writing it back into the other form might help you. Anyways, moving on. Here's a really hard looking problem. Is it a hard problem? I mean, in the form that it's currently written in, sure. The key to this problem is recognizing that x to the 5th power divided by x to the 30th power is the same as 1 over x to the 25th power, which is the same as x to the negative 25th power. Go through those steps slowly and make sure you see why that's all true. Similarly, x times the square root of x is the same as x times x to the 1/2 power, which is the same as x to the 1st power times x to the 1/2 power, which is the same as x to the 3/2 power. Trust me, you want to go through these slowly and convince yourself of these facts. If you're good with these two facts, we can rewrite this problem and we can take the derivative. Since x to the 5th over x to the 30th is the same as x to the negative 25th, I can replace this expression with x to the negative 25th, and similarly, instead of writing x times the square root of x, I can write x to the 3/2 power. Ooh, and 9 times 2, that's equal to 18, right? Yeah, it is. And if you want to make this 18, you can. Or if you want to leave it as 9 times 2, you can. It really doesn't matter. This term is a constant. When you take its derivative, it's going to be 0. Doesn't matter if you leave it as 9 times 2 or 18. It'd be really weird for me to ask the question with the 9 times 2 here, because I might as well just write the 18 here. The only reason I wrote 9 times 2 is to try to be a jerk, to try to confuse you, to try to make you think that this was something other than just a constant, to try to make you think that that matters. It doesn't. Let's take this derivative using the power rule. Negative 25x to the negative 26 power minus 3/2 times x to the 1/2 power plus 0, which you don't have to write. And then if you feel the need, you could rewrite this as negative 25 divided by x to the 26th minus 3 times the square root of x divided by 2. Either of these are perfectly sufficient answers. The trick in this example, as it's been in most of these examples, is just rewriting the question in a form conducive to our rules. And guess what? Same thing's going to happen here. Suppose we're taking the derivative of 2x plus 1 squared. This one's really tricky. You might think that you can use the power rule on this too somehow, like bring this down in front of the whole thing. You can't, or at least not yet, not without this thing called the chain rule that we'll learn in about a week or so. Okay, if I can't do that, what can I do? Well, when you're squaring something, it's the same as multiplying it by itself. So you can think about this problem as the derivative of 2x plus 1 times 2x plus 1. And you're like, I got it from there. Then I just take the derivative of this and the derivative of this and multiply those together. No, the derivative of a product is not the product of the derivatives. Remember, we do not have a product derivative rule yet. The derivative of a product is not the product of the derivatives. I can't emphasize that enough. Okay, then what do I do? If I can't take the derivative of a product, what can I do? We'll get rid of the product. Expand this. We're still not doing any calculus at all. We're just rewriting 2x plus 1 squared as 2x plus 1 times 2x plus 1, which we can then FOIL to get 4x squared plus 4x plus 1. All of a sudden, this problem went from a hard, tricky thing to something super easy. The derivative of 4x squared plus 4x plus 1, I mean, you probably don't even want to show any steps at this point. That's 8x plus 4 and we're good. If you're at all unsure about this 8x plus 4, please write a couple lines in between here and here. Use your derivative sum rule, saying the derivative of this thing is the derivative of this, plus the derivative of this, plus the derivative of this. Then pull the 4's out in front and take your derivatives, and you'll see you'll get this answer. If it's not 100% obvious how this line is equal to this line, show steps in between. Trust me, it'll make your life a lot easier. It might seem like more work, but it's actually less work. I think we got one left. It looks really hard. We have some implied multiplication because of this squaring, and then we also have some division, and we don't have derivative rules for multiplication or division. It's really tempting to look at this problem and think, it's easy. The derivative of 2x plus 1 squared, I just figured out that's 8x plus 4. And I know that the derivative of x is just 1, so this answer should just be 8x plus 4. Yeah, that'd be nice, right? But it's not, because the derivative of a quotient is not the quotient of the derivatives. It would be really cool if it was, but it's not. This is not equal to this. This is not the right answer. What you have to do is rewrite this in a form that's conducive to your rules. So maybe first expand the top. We get 4x squared plus 4x plus 1 divided by x. And then get rid of this division. How do you get rid of this division? Well, we can think about this as 4x squared over x plus 4x over x plus 1 over x. Wait, what just happened there? You can break up a fraction when the numerator has multiple terms into multiple fractions. Oh, I didn't know you could do that. Well, yeah, you did, because you can go from this step to this step. If you had the same denominator and you're trying to add up those fractions, you just add up the numerators, right? If you can see that this is the same as this, maybe that justifies why this is the same as this. But I know from experience that most students are a lot more comfortable going in this direction than they are in this direction. Okay, you rewrote the problem, but I'm still not sure I can take the derivative. Yeah, we still got to simplify more. 4x squared divided by x, I can cancel this x and one of these x's, and it's just the derivative of 4x. 4x over x, I can cancel out the x's, and that's just the derivative of 4. 1 over x, I can rewrite that as x to the negative 1 power. No calculus anywhere in here. All we're doing is algebra and rewriting the question. The first time we use calculus is right now. The derivative of 4x is just 4, because we pull the 4 out in front, and the derivative of x is just 1. The derivative of this 4 is just 0, which you don't even have to write. The derivative of x to the negative 1 power, you take that negative 1 out in front, and then you'd raise x up to 1 less than negative 1, which is negative 2. This is an okay answer, but you can clean this up a lot. I mean, at a minimum, you don't need to write plus 0. And when you have a 1 as a coefficient, you probably don't want to write that either. Maybe we just say 4 minus x to the negative 2 power. Or if you really didn't want to write this with negative exponents, 4 minus 1 over x squared. There's a lot of examples, and you might think that we just did a lot of calculus, but I might argue that we didn't do a lot of calculus. I'd argue that we did a lot of algebra and very minimal calculus. Almost all of the challenges in these 8 examples that we just did was the algebraic portion of it. Rewriting a given question in a form that you can use your rules on is a big challenge, and it takes a lot of practice, hence these 8 examples.